Okay, we want to talk about matrices and linear combinations of vectors. So we have a set here of 3 vectors in R2. And we could sketch these vectors in R2. 2, 1 goes out that way, negative 3, 2 goes back this way, 4, 5 goes out that way, but it's a little steeper than this one. Okay, we could sketch them. We can form a linear combination of these vectors. A linear combination is just a sum of multiples. So we could take any 3 numbers and multiply by these vectors and add them. We understand that corresponds to making a vector longer or shorter than this one, depending on the number that we use, and maybe in the same direction or opposite direction, depending on whether we choose a positive or a negative number. And same thing for this one, same thing for this one. So we get 3 vectors, might be this way, and this way. And then we add those vectors. And we can add those vectors just graphically, geometrically. All the numbers are whole numbers, so you could do this on a grid. Okay, very easy. So we understand that this linear combination is just a sum of multiples of these 3 vectors. So let's say the multiples are 3, 2, and negative 4. Then now we have a specific linear combination of the 3 vectors. Now over here, we do the whole thing symbolically. We let V1, V2, and V3 be our 3 vectors. And maybe we mean the same vectors here. And maybe we mean 3 different vectors. The multiples, we could choose any variables we want to stand for the multiples, or any letters we want, or symbols. It could be alpha, beta, gamma. It could be Z, Q, and R. Okay, it could be any 3 letters, and put them in front of these and connect with plus signs. To keep things straight and to keep the notation as simple as possible, it's good to use subscripted variables. Subscript 1 here, subscript 2 here, subscript 3 here. These numbers are going to be constant, so C is not a bad letter to use, and it's almost universally used in this context. So we have C1 V1 plus C2 V2 plus C3 V3. It's another sum of multiples. It's another linear combination of these 3 vectors. Okay, well, let's see how it works out over here. Okay, so we can write this linear combination, and I'm going to claim that we can write it by simply taking these 3 vectors and putting them in columns. So we can do 2, 1, and of course it's 3 times 2, never mind. Pretend I didn't do that. Okay, it's 2, 1. Let's see if we can get rid of all traces. Well, okay, I guess I'm stuck. Okay, so anyhow, it's 2, 1, and then negative 3, 2, and 4, 5. We put those as columns in a matrix, and then we can multiply that matrix by 3, 2, negative 4. And that works because we're going to get, when we do the first row by the column, we're going to get 3 times 2. When we do the second row by the column, we're going to get 3 times 1, which is exactly what we get up here. And when we do the first row times the column, we're going to get negative 3 times 2. Second row times the column is going to give us 2 times negative 4. Okay, well, there's our 3 times, negative 3 times 2. And our 2 times, I said 2 times negative 4, 2 times 2. Okay, so we see that we get this product, and similarly we get this product from the third row, and of course then we add everything up. Well, let's just see how that looks. Okay, so this is just doing row times column, 2 times 3 minus 3 times 2 plus 4 times negative 4. That's our first row times a column. Our second row times a column is 3 times 1 plus 2 times 2 plus 5 times negative 4. Okay, and again we see we have I really, to keep things straight, I wrote this a little bit carelessly. It's right, but we want to do this as 1 times 3, so I can point out what I want to point out here. That we have 3 times 2, 1. Okay? Here we have 2 times negative 3, 2. Here we have negative 4 times 4, 5. So we have the whole sum that we would need here, but it's sitting right here in front of us. Well, we can then add that up, and we get 6 minus 6 minus 16, and we get 3 plus 4 minus 20. Okay? And that equals negative 16, negative 13. Now, it shouldn't be surprising if we do the calculation here. 3 multiplied by 2, 1. And let's make sure that I'm getting this on the camera. Okay, 3 times 2, 1. Plus 2 times negative 3, 2. Minus 4 times 4, 5 equals 6, 3 plus negative 6, 4, just multiplying through here, minus plus negative 16, negative 20. Well, that equals 6 minus 6 minus 16, 3 plus 4 minus 20, which is identical to what we had here. And it should be obvious why that is. We want to make sure we understand where all these numbers go, where they come from, and what they mean. But then this comes out as negative 16, negative 13, and that's a badly written check mark, but this matches this. Let's make sure we got a decent sized negative here. Okay, well now, if we go up here, how are we going to write this product? Well, we do the same thing. Okay, so first of all, okay, the matrix with V1, V2, V3 listed here, no commas, denotes a matrix with columns V1, V2, and V3. Okay. So V1, V2, V3 multiplied by the column C1, C2, C3 for reasons that we saw over here. C1 is going to multiply everything in the first column because that's the way rows multiply columns. Okay, the 2, 1 both get multiplied by 3. Once when we multiply the first row, once when we multiply the second row, and we see how that works out. So we have C1 V1 plus C2 V2 plus C3 V3. Now, it's important to understand that this works no matter how long your vectors v1, v2, and v3 are. So it works no matter how long the vectors v1, v2, v3 are. We still just have 3 columns, so we only have 3 numbers in each row to multiply by the 3 numbers here. Doesn't matter how long the columns are, as long as they're the same length, of course, because we can't form a linear combination of 3 vectors unless they're compatible for addition. So they all have to have the same length. Okay. This is a very important notation. Very important to understand this. So, make sure you do.